We've seen how the k-means algorithm works, and we saw that it has two issues. The first is that we have to specify k, the number of segments that you're looking for. And the second is that it may be sensitive to the initialization of the k-means. This method, called mean shift, mitigates these two problems. So let's take a look at how it works. So here is your pixel feature distribution. We're going to show this for convenience for visualization purposes in 2D. Let's assume that when you take all your pixels and you map them to feature space, you get this distribution right here. You can see that this distribution has varying density. This is highly dense, and this is less dense right here. So you can represent this as a normalized density function that looks like this. These two axes correspond to your features. The third axis is telling you how dense the distribution is. So now, one can see this as a function which has hills, and each hill represents a cluster that we are looking for. And the peak or mode of the hill represents the center of the cluster. So what we're trying to do is essentially have each pixel, based on its feature value, climb the steepest hill within its neighborhood. So what does that mean? Let's take this pixel right here, sample pixel. The steepest hill is this one, so we want to make this pixel so-called climb the steepest hill as such. That's the pixel climbing the hill. And once it's climbed the hill, the pixel is assigned to the hill that it climbs. So basically it's going to climb the hill and end up at the mode of that particular hill or the center of the hill. And that is the cluster or hill that the pixel is assigned to. That's the idea behind mean shift. So if you're able to do this, then you end up with clusters that look something like this. So each cluster is given a different color here. Also shown are the peaks of the hills. So now let's take a look at an algorithm for achieving this. It's actually a very simple algorithm. Let's assume that you're in a two-dimensional feature space. Again, it doesn't have to be two-dimensional, it can be high-dimensional. And let's say that this is a sample pixel. We want to find the hill that this pixel belongs to. In other words, the cluster it belongs to. So what we're going to do is view this pixel location as the mean value for that pixel. So if you simply take that pixel, its mean value is its current location itself. And then we're going to take a window around it of some size. Let's say the radius of the window is W. So window of size W. And we take all the points in the distribution that lie within this window, and we're going to calculate the centroid or the mean. It could be just a simple mean of all of these points, or it could be a weighted mean. Doesn't really matter. By weighted mean, what we mean is that the closer to the points are to the sample pixel, the current location, the higher weight they get. So you're actually reducing the effect of things that are further away from the point. In any case, you end up finding the mean, and that mean, let's assume, is this green point right here. So then you're going to move to that green point. So that is the vector by which you move, and that is exactly why the method is called mean shift, because the mean that was previously here has now been shifted to this new location. Hence the term mean shift. And now we're going to repeat the process. We're going to do the same thing. Compute the mean, the new mean using all the points inside this window in its new location. And we then end up moving to that location. Keep repeating the process. You're going to end up climbing the steepest hill in your distribution. You end up there, and perhaps finally you're going to end up there, at which point you're not going to move any further. If you recompute the mean, it doesn't give you a mean that is away from this point. You're stuck there. That then becomes the mode or the peak of that hill. So then That's what this pixel is going to be assigned to. It's going to be assigned to this mode. But since that hill is shared by many other points, you're going to get other points that climb the same hill and end up at that mode as well. So features that converge to the same mode belong to the same cluster. That's the idea here. So here it is in terms of an outline of the algorithm. You're given a distribution of n pixels in feature space. You want to find the modes or clusters of the distribution. So you're going to start off by setting the mean value of a feature to be itself. Mi is fi. That's the initial mean for the pixel I. And then you're going to repeat the following for each mean mi. You place a window of size w around mi. Then you're going to compute the centroid m within that window. And then you're going to set mi to that new centroid, the new mean. And if the mean does not shift, that is, stop, if the shift in the mean mi is less than some threshold. If that happens, then mi is the mode. And so you label all pixels that have the same mode as belonging to the same cluster. Very simple algorithm. And so let's take a look at how well this works. So here is an example of some data which comes from some experiment. And in this data, you essentially have 3 clusters, but they're already labeled here. So you have 3 main clusters. All the circles here, they belong to one cluster. All the pluses here belong to another cluster. And then you have your crosses, which belong to another cluster. And then you also have these squares, which are scattered all over the place. If you apply k-means, and you see that you have k or 3 dominant clusters here. So if you use 3 means, you end up with this result, this clustering. You do fairly well, but for these points right here, you've obviously misclassified them. These get assigned to this cluster, and these get assigned to this cluster. In contrast, if you use mean shift, you get a very nice clustering. So you see that it's very close to your desired result right here. So let's see how this works with image segmentation. So here is our simple example again, the peppers. And this is what we got with k-means by using R, G, B, and XY. So it's a 5-dimensional feature space using a k value of 16. So we've asked for 16 clusters in this case. Again, I should remind you that 2 things that are far away from each other could belong to the same cluster. So you have to look at the colors here. And then if you apply mean shift, you get a fairly nice segmentation. This is mean shift applied with a window size of 21. Remember, we don't specify k in this case. K is naturally discovered by the method, but what you do need to specify is the window size, and that's 21 in this case. Here are some other examples, more challenging ones, landscapes. You see that you get fairly nice segmentations. Of course, one can argue as to whether these are perfect segmentations or not. In fact, we probably wouldn't agree on what really is a region in every case here, but these seem like fairly reasonable segmentations using mean shift. So a few comments about mean shift. Very simple, but actually computationally somewhat expensive, because for every one of these points, the hill climbing process is quite expensive, because for each new mean location, you've got to recompute the mean, and you've got to do that for every pixel in the image. But on the upside, it's able to find an arbitrary number of clusters. And there is no initialization of means, as in the case of k-means, necessary. It's fairly robust to outliers. The only parameter that one needs to choose and that the algorithm may be sensitive to is the window size W.